Okay, good morning. Today we are going to be covering the week 3, which is sorry, go to home page. What happened? Yeah, so today we are going to be covering week 3, and week 3 is supposed to start with LTI invariant systems. We are going to be doing the introduction, response of continuous time LTI system, the convolution integral, the properties of LTI, continuous LTI systems, and also going to deal with a discrete time LTI system. So that is our subject for today. And of course, we start off with chapter 2, which is LTI systems. And we say now that the two most important attributes of systems are linearity and time invariance. In this chapter, we develop the fundamental output or input-output relationship for systems having these attributes. And it will be shown that the input-output relationships for LTI systems is described in terms of convolution operation. So the importance of convolution operation in LTI systems stems from the fact that knowledge of response of an LTI system to the input impulse response, that is very important, that right there, that if we know the response of an LTI system to a unit impulse system, then we can always find its output given any input signal. So specifying that input-output relationship stems by systems by differential or difference equations is what we are going to be discussing in the data section of this class. So to start with, we are going to start with the response of a continuous time LTI system and the convolution integral. And the first thing is we must be able to characterize a system by its response to the unit impulse response. And as you can see, equation 2.1 is the description or that is describing the response of a system given the input is a unit impulse response. So that serves as an introduction, and so we are saying that we can always write the unit the impulse response in terms of how it treats a unit impulse response. And of course, that is the one we define as the impulse response h of t. Now, the response to an arbitrary system, if we know the h of t, becomes very simple because it is described by equation 2.2. And we are saying that consider an input. Okay, there's something we said earlier that any arbitrary input signal can be described as an integral, which is described in equation 2.2, that x of t can always be described as the integral from minus infinity to infinity of the signal itself, but with the integral with respect to t d tau. Sorry. With respect to d tau. So this is the one that we refer to as the convolution integral, and it is very useful. Convolution integral, it is very useful in describing the any input signal xt in terms of its in terms of a unit impulse response. That is something we have already seen before, therefore we don't need to go there far too much. Now, since the system is linear, then so we have described this as our input signal, and therefore we want to describe the response of a system y of t given the arbitrary signal x of t. They are saying that equation from this equation, we're saying that y of t is equals to what the system response, or what the system does to the input signal, which is described by the function t. And you're saying now that since we described x of t with this integral, therefore we can put the t function inside the integral to have that y of t is equals to minus sum of um, the integral from infinity to minus infinity to infinity of x of tau from this equation. Then it is now acting on the function of time dt minus tau d tau. So that becomes, so how this system acts on the unit impulse response can simply be classified, be expressed as we can see this equation that and therefore what we are saying is that this the continuous time LTI system described by this function right here, acting on unit impulse signal, can be evaluated as the convolution which gives us the input, the output signal y of t. So in few words, we are saying that if we know the continuous time LTI system, what it does, or how the output behaves when the input is a unit impulse response, then you can just convolve that with the input at time tau, and therefore evaluated from minus infinity to infinity, and that gives you the output for an arbitrary signal x of t. So that is what is described by equation 2.3. And therefore we are saying that since the system is time invariant, we are saying that equation 2.4 simply describes the continuous time behavior of the system for given a unit impulse system. And therefore, this h of t minus tau is simply the function that acts on unit impulse dt tau as it is. So that is equation 2.4. And if we now substitute equation 2.4 into 2.3, it's something that we get that y of t for will be, that is the output, will be a function of the input signal integrated over tau and convolved with the impulse response ht minus tau d tau. So that is the description, that if we know the behavior of a signal which is described by the impulse response h of tau, and now we have an arbitrary input x of tau, and therefore we can always be able to determine the output y of t for a given arbitrary signal x of tau. So having said that, we see now that the equation 2.5 indicates that a continuous time LTI system is completely characterized by its impulse response h of tau, h of t. So we are saying that if we know this system and you input an input x of t, which is equals to d of t, then this is the LTI system. The output that you get here, which is h of tau, h of t, can always I'll assist you to describe the system even when you have x of t being an arbitrary signal, and that is not necessarily equals to d del t. So when the x of t is arbitrary, you can always be able to describe the output y of t, because we have h of t, which we are saying that we normally convolve from minus infinity to infinity, and you have your arbitrary signal, and then this is just a convolution integral with respect to tau. So actually now that takes us to the third point, which we discussed the convolution integral. They are saying that equation 2.5 defines the convolution of two continuous time signals, x of t and h of t, which is denoted by equation 2.6. And equation 2.6, just a minute. My mouse is stopped for the minute. So we talk about now the convolution integral, which we are saying that equation 2.5 that we have defined up there defines the convolution of two continuous time signals, x of t and h of t, denoted by y of t equals to x of t, and the sign for convolution is right there, which is a star. So you're saying that y of t can always be described as x of t convolved with h of t, and that is the definition of the convolution integral. And as we have seen, that simply describes how you define convolution integral in time domain or in continuous time domain. And that is what is seen in equation 2.6. Now, equation 2. We're saying that equation 2.6 is commonly referred to as the convolution integral. And thus, we have the fundamental result that the output of any continuous time LTI system is the convolution of input x of t with the impulse response h of t of the system. So once we know the impulse response of the system, which is described by h of t, then you can always be able to describe the output of any continuous time system given the input x of t, which is defined by this convolution symbolized as with a star x of t star h of t. And therefore, we're saying that if the input is del of t, it goes through our LTI system, then the output is the impulse response. So this is the unit impulse, the unit impulse signal described by del of t, and therefore when the input is the unit impulse signal, then the output is the one that you describe as the impulse response as h of t, and therefore when we have an arbitrary signal x of t, that means the output will be convolution of x of t with h of t, as you can see in that equation right there. And now that allows us to move to section D, which are going to look at the properties of a convolution integral. And we can say that the first property is that x of t convolved with h of t is the same as, you can always interchange it's competitive. That is what competitive means, that x of t, h of t convolution is the same as h of t convolved with x of t. Remember, this is different from vectors. We said that a vector A multiplied with B is not the same as B and A. Or if you have this, assume this is a cross product, this is a cross product. So assume this is never the same, and you normally say that they are not commutative. But for the convolution integral, we're saying that the commutation is positive. And the other thing is associative. Associative means that you can take the bracket at that point, perform the convolution for these two, and then convolve the output with h of t that is outside. We are saying that it is the same thing as though you did the convolution between h1 and h2, and then convolve with the outside x of t. So that will still be positive. And last but not least, that it is distributive, which means that you have this bracket between two impulse responses of two systems, and you have one input. That means that the output will be the same as though the input passed through the first system and then added or summed to the output that went or the input that went through the second system, h1 of t. This property can be described by an input being going through two systems that have impulse response h1 of t, and another system right there that has impulse response h2 of t, and then you sum them through a summer, then the output will be y of t. I think here you normally say this sum, this is your input x of t, and therefore this is convolution that is coming out of one x1 x of t convolved with the h1 of t, and the same thing as x of t convolved with h2 of t. So that serves as to describe the properties of the convolution integral, and therefore we want to look at the convolution integral operation, how it happens. And we are saying that applying the property, the commutative property 2.7 of the convolution integral of the convolution to equation 2.6, we obtain that y of t is equals to ht convolved with x of t, and we can say it is described by equation 210. And there's some properties here that are worth looking at, and they are just describing how you would physically or graphically resolve the value of h of t minus tau, but vis-a-vis if you are looking for x of t minus tau vis-a-vis h of tau. So these properties are just describing how you perform that operation, and it is more or less what we have already described in the previous section. So we jump now to the step response and say now that the step response is now we have been dealing with the impulse response, and therefore what we want to deal with now is step response. And a step response is the one that we described with the symbol u of t, and we are saying that a system, that how the system behaves when the unit step or step input is applied is the one that is called the step response, and it is described by symbol st. So when the input is u of t, and if you can remember, the u of t was described as starting at 0 to have a positive 1, and as t progresses, it maintains a constant value. This is the function of u of t, but in to the left of 0, the value of x or u of t remains to be 0. So now in that case, we want to say that we can uniquely describe the output of a system if we know its step response. And it's saying now that the step response st of a continuous time LTI system represented by t is defined to be the response of the system when the input is the unit response, the unit step input that is described by ut, and that is described by equation 211. Now, in many applications, sorry, my, sorry. Sorry for that. I think we can move on. We are saying that my screen that was misbehaving. We are saying that in many applications, the step response ST is also very useful in characterizing the system. The response ST can be easily determined by equation 210 such that assume we have not added this stuff that I think I was adding when I was doing some other things. So we are saying that assume that the step response ST, we are saying, okay, of course, that is what you're saying, that it's a very useful characterization of the system. Therefore, the step response ST can be determined from equation 210, that is ST is equals to H of T. We are now assuming that the arbitrary input that was described by equation 210 is not x of t now, or rather the x of t is equals to u of t. And we have said the output in that case will be the s of t, the one that we are calling the step response, and is simply described by what we have. We are just reproducing equation 210, except where we are now replacing our x of t with was our x of t, the one that we said x minus tau in our convolution integral. Now it stops being x of t minus tau to being u of t minus tau. And we are saying that this equation 212 simply means that the integral changes, because we know this equation is described by an integral from minus infinity So sorry, I think there's some things I have deleted. I think I'm supposed to be here. We are describing how you can transition from having this equation to becoming this, and the idea is just remember that u of t is defined as being equals to 1 when t is bigger than 0, and it is 0 when t is less than 0. So what we are saying is that we want to transform this integral to only when u of t is equals to 1. It is saying that it is defined as uh of tau u of t minus tau d tau. What we definitely know is that this equation can only make sense. This term will be equals to 1 if the term in the bracket, if t minus tau is greater than 0. So what we want to do is to take this t on that side and say that minus tau is greater than minus t, and if you change the sign, you are going to have tau is less than t, because how we change that bracket is because you can say divide by negative, this goes changes sign becomes less than, and this changes sign becomes positive. So we are saying that this will be 1 only when tau is less than t, and therefore for this integral to make sense, the upper integral will only make sense if tau is less than t. Therefore, the upper limit will be t, and therefore once that upper limit is t, this becomes 1, and therefore we are left with minus integral of t minus integral from minus infinity to t h of tau. The other term becomes 1, therefore d tau, and therefore that is how we are able to transverse or to change equation 212 to have this on our right term, and this is the one that we described as the step response. So thus the step response st can be obtained by integrating the impulse response h of t, just like we have seen that if we integrate the h of t, we are able to get the step response. That is a very important realization, because this is what you're saying, that you are able to get the step response s of t if we just integrate our impulse response which is h of t, and that is a very important realization. So of course we move on to the next section, which of course there's something else. If we differentiate s of t, we are able to get h of t. So that is the other side of our equation, that if we differentiate s of t, we are always able to get our h of t back. Therefore, the relationship that exists between the impulse response and the step response is simply the h of t is the derivative of s of t, and of course the s of t is the integral of h of t. Now we are going to talk about the properties of continuous time LTI systems, the systems with or without memory. That is our first item. So we just needed to find out how a continuous time LTI system behaves, or when it is said to have memory, or when it is said to have no memory. It is saying that since the output y of t of a memory-based system depends only on the present input x of t, then if the system is also linear and time invariant, this relationship can be described to be of the form 2, 1, 4, as you can see in at this point. Therefore, where k is considered to be a constant or gain, and thus the corresponding impulse response h of t is simply said to be equals to be producing. Of course, it's a gain that is sampled by our impulse response. And therefore, h of t, if h of t naught is not equal to 0, where t naught is not equal to 0, the system is said to have memory. That means, what we know is that, I think we can just do that very quickly. We said that delta of t will have a value of infinity when for t is equals to 0, and we'll have a value of 0 for t is not equals to 0. So what we are saying is that if h of t naught is not equals to 0, for t we expect it. Of course, we say we expect when t naught is equals to 0, we expect h of t0 h of t0 to be equals to 0. So if it is not equals to 0, then the system is said to have memory. I want just to repeat a few things I have said about this. That we are saying that system without memory is described as y of t being equals to k x of t, where x of t is an arbitrary input. But if you remember, we said that k is the function that is acting on the input, and therefore the impulse response of our LTI system or continuous time LTI system, h of t, can be described to have the same k acting on our unit impulse input, so signal, and therefore since this is our impulse response h of t, if h of t is not equals to 0 at t equals to 0, then we are saying that this is this system has memory. The next item that I want us to discuss is causality. That causality is we want to wrap this. The next item I want us to discuss is causality, and you're saying that as discussed in section 1.5d, a causal system does not respond to an input event until the event actually occurs. That is, a causal continuous time LTI system, we are saying that h of t will be equals to 0 if t is less than 0. So before the event occurs, the impulse response will be 0. Now, if you apply the condition 2.6 section 210, the output of a continuous times LTI system can simply be expressed as equation 17. So if you remember, we are saying that y in equation 210, y of t is equals to minus infinity to infinity h of tau x of t minus tau d tau. Now we are saying as long as time or the event that is introducing our input x of t has not aligned, all events start at time is equal to 0. So for any time less than 0, therefore x of t will be 0. And therefore, we are saying that that system, for it to be causal, then it must start at t is equal to 0. So what we are saying is that we are going to change our limits of the integral from minus infinity to infinity, and therefore that constitutes what we now refer to as a causal system. So the next item we want to discuss is stability. And stability says that a system is stable if it is bounded input, or the bounded input, we normally call it BIBO, that a bounded input produces a bounded output. There's something we normally mean by that, that if x of t is less than infinity, that means it is bounded, then y of t will be less than infinity. That means that this is bounded and this is bounded. That means the system that is acting on this, which is described by h of t, or the impulse response, then is said to be stable. The next item I want us to discuss is the eigenfunctions of a continuous time LTI system. And before we discuss this, I want to probably remind you what eigenfunctions means. And I have prepared this quick introduction to eigenvalues, what it means. We normally say that we have an eigenvalue equation that is described by an operator that acts on a function ft, or which can be defined by psi, will always give you a constant value that we describe by omega, and it gives you the same function that you had psi. So we are saying that you have an operator that acts on a function ft, then this function produces an eigenvalue lambda that will still act on the function your ft. So that is, this is what we refer to as the eigenvalue equation, and we are saying that we can always have different operator that acts, okay, any operator that, or any function that acts on a function ft producing an eigenvalue lambda that is a constant, which can multiply the same function ft to give us our original operation. That means that we have satisfied the eigenvalue equation. And we can have an example that we can use these symbols, and I think these symbols sometimes might confuse you. This is ohm describing the operator. In this case, I have used the t to describe the operator, and then psi might be used as our function, which I have used in the case of ft, and you're saying that the constant omega, I've used another one that is called lambda, and you're saying that it is good to give the same function psi that I have given you at that point. So this function is always dependent, and for us it is the one that is describing our the operation that we are describing our system with. So for now, we are saying that, for instance, let your function be a differentiation, or you want to find the derivative of your function ft of for a function that which we have defined to be psi equals to ex, or exponent of, or e exponent of God, what do you call this? ex. Say that the natural number raised to ax. This is the exponential, the exponent that we normally express as such. So we are saying that if this is your function, then and you want to derive it, to differentiate it with respect to x, then d dx is the operator ohm, or the one I've also called t. Then you're saying that if it acts on this function f of x, it will give us a constant a, and the constant a will multiply with our original function ex, and therefore we are saying from this equation that this equation that we defined up here is satisfied, and therefore if the eigenvalue equation is satisfied, then we say that exponent of ax is an eigenfunction of operator d dx having eigenvalue a. So we are going to see shortly that we can do the same in our equation. So that was meant to just serve as an introduction to the eigenvalues and eigenfunctions. So what we are saying is that we said that a continuous time LTI system represented by T has, or rather, in chapter 1, we saw that the eigenfunctions of continuous time LTI system represented by T are complex exponentials E of St, where S is a complex variable. That is, that if your system is T, described by a function T, and you have input E of St, then it will give you an eigenvalue lambda and still give you the same function EST. Therefore, where lambda is the eigenvalue of T, being our impulse response associated with the eigenfunction EST, and therefore we can set that our input E of St, we will have the output as such. So let's do that a bit slowly and see how that comes about. So we are saying that assume you have an impulse response h of t that is described by t, and you have an input x of t, which is equals to e s of t, and therefore your y of t, we expect it to be h of t convolved with x of t. And the integral function of this equation, if we assume it to be causal, we're going to start from 0, and then we are going to say h of tau x of t minus tau d tau. And now we are saying something here that is very important, that if x of t is now replaced by this, we are going to say that our integral will take the shape h of tau e of s t minus tau d tau, and there's something we can do to that equation. If we remove this term that is not dependent on tau, we are going to have an equation that takes the form e s t from 0 to infinity h of tau e of minus s tau d tau. And this is what we have here, and this is what we are referring to as the eigenfunction of our input so we are saying that from what we have just done, we are saying that h of s is the eigenvalue, which is equated to lambda and is assumed to be constant because our integral that is with respect to tau is considered to be constant. So thus the eigenvalue of a continuous time LTI system associated with eigenfunction E of St is given by h of s, which is a complex constant whose value is determined by the value of s by equation 224. And we note that equation 223, that from equation 223, that y will be 0 if y at time 0 will be equals to the eigenvalue h of s. and this problem can be seen at problem 1.44. The above results derive the definition of Laplace transform and the Fourier transform that we will be discussing at a later stage.